In this video, we're going to talk about measures of center. So specifically, we'll talk about the mean, median, and mode for ungrouped data. A measure of center is a value that represents the center or middle of a data set. The mean, or average, of a data set is the value found by adding the data values and dividing by the total number of data values. So notationally, the mean is equal to the sum of each of the data values divided by the total number of data values, or the sum of data values divided by the number of data values. So the mean is a fairly clear concept. We might not need to use this notation to think about it, but we will be using similar notation throughout the course. So I just want to break down these pieces of notation right now. So sigma is the Greek letter sigma. It's pronounced sigma. It's a capital Greek letter S, and this means add together objects of this type. So whatever kind of object comes right here, we add together all things of that type. Lowercase x is usually used to represent individual data values. So represents individual data values. So in this case, we're adding together all things of this type. The individual data values we're adding together. Lowercase n usually represents the sample size, or the number of values in a sample. So lowercase n is the number of values in a sample, and uppercase n, which we don't see above, is the population size, the number of values in a population. So if we were talking about Americans, the population size would be 330 million. If we were taking a sample of those and finding the average of a sample, its sample size would be whatever that average was, or whatever that the number of values in the samples happen to be. So maybe we sample 200 adults, we poll 200 adults, and in that case, lowercase n is 200, and uppercase n, the population size, is 330 million. Okay, so how does that relate back to the mean? The mean of a sample, so the mean of a sample is denoted by x with a bar over it, and it's equal to what we have written above, the sum of all of the x values, the sum of all the data values divided by the sample size. And the mean of a population is the same thing, but we use a different different notation for it. We call this mu, and this again is the sum of each of the data values in the population divided by the size of the population, capital N. So a couple things to note here. If this is the mean of a sample, this is based on a sample, and therefore this is a statistic. Whereas this is the mean of a population, it would be based on data collected from every member of the population, and if that's the case, then this is a parameter instead of a statistic. What else to note? Let's also just talk about pronunciation real quick. So this is pronounced mu, or like what a cat might say, mu. So that is how to pronounce that Greek letter, which is kind of like a curly letter M. And this is typically pronounced x bar. So people just say x bar, or the sample mean. Okay, so let's look at an example together. So below are salaries of 8 NCAA football coaches. These were selected by me from USA Today in 2019. So these are not all of the NCAA football coaches, but just a sample of them. And we want to find the mean of this sample. So we want to find the mean of this sample. The sample mean is denoted x with a bar over it. X bar is equal to the sum of all the data values divided by the total number of data values. So in our case, the sample size n is equal to 1, 2, 3, 4, 5, 6, 7, 8. There's 8 data values, so we divide by the sample size, which is 8. N is equal to 8. And on top, we would have the sum of each of the data values. So it's the sum of 700,000 plus 3,500,000 plus ... We could write all those in, or we will be writing each of those values in, but we're adding each of those values together. So plus 440,000 plus 680,000 ... plus the last value is 1,600,000. So we're adding those data values and dividing by our total. So at this point, I would probably pull out a calculator to add the values in the top. So adding the values in the top together would give me 17,675,000. And then this is still divided by 8. And so I could then divide by 8. And this would give me 2,209,375. So that would be the mean, or the sample average. So this is our sample mean. Now let's talk about another measure of center called the median. The median of a set of data values is the middle value when the original data values are arranged in order from smallest to largest. So if there are an odd number of data values, there's just one value in the middle, and that's the median. So in the first example, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. N in this case, the sample size, is equal to 9. And so there will be just one middle value. So if you look at 1, 2, 3, 4, 5, the fifth value, we have four values on this side and 4 values on that side. And so that means that the value 15 is in the middle, and our median in this case, which is denoted x with a tilde over it, x tilde, the median for this example, is 15. If there's an even number of data values, so in this case below, n, the sample size, is equal to 10. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data values there. And there's going to be 2 data values in the middle. So half of 10 is 5, 1, 2, 3, 4, 5. And so we've got, at that bar, we've got 5 data values on the left and 5 data values on the right. So 5 data values below that bar and 5 data values above that bar. So no one value is in the middle. So what we do is we take the average of these 2 values. So we take the average, 6 plus 8 divided by 2 is 7. And so in this case, our median is that value, x tilde, or the median, is equal to 7 for this set of data. Okay, so there is a formula that we could use to figure out what the median is in each case in terms of the sample size n. In particular, for n being an odd number, like 9, the median will be the n plus 1 over 2, n plus 1 over 2th data value. when the data is arranged in order. So in our case, with n equals 9, so when n is equal to 9, n plus 1 over 2 is equal to 9 plus 1 over 2. That's 5, so it's the fifth data value. And yes, this was the 1, 2, 3, 4, 5. This was the fifth data value. When n is even, then the median will be the average or the mean of the n over second and n plus 2 over 2th data values. So it's the mean of the two middle data values, and those two middle data values will be the n over second data value and the n plus 2 over 2th data value. So in our example here, again, n was 10, and so n over 2 is 10 over 2. That's the fifth data value. And n plus 2 over 2 is 12 over 2, the sixth data value, just the next one. And so we can see that, yes, this in fact is the fifth data value, and this is in fact the sixth data value. This data is already arranged in order. So 0, 1, 2, 3, 4, 5, 6, those two data values, we're taking the average of those. So you don't necessarily need those formulas if you're dealing with a small data set like those two, but if we were dealing with a larger data set, we could refer back to those two formulas. Okay, let me give you an example to try for finding the median. So let's look at the data that we used earlier to find the mean. This sample of 8 football coach salaries. And let's find the median for this sample. So give this a try. So pause the video and try this out, find the median, and we'll talk about it in just a moment. Okay, so we want to find the median of this sample of 8 football coach salaries. So we want to find the middle value when the data is in order. We could start by putting the data in order if we wanted to. If we do that, then we've got, okay, this is the first data value in order. This is the second data value, the next largest. This is the third data value, the fourth data value, the fifth largest one, the sixth largest, the seventh largest, and the eighth largest. So those are our data values in order. And now we say, okay, which ones do we need? So this is n equals 8 is the sample size. This is an even number. And so we're going to have 2 data values in the middle. Specifically, the n over second data value is the fourth data value. And the next one up, we could use n plus 2 over 2. That's 10 over 2. That's the fifth data value. So the fourth and the fifth data value are going to be our 2 middle values. And so we should find the mean of the fourth and fifth value when the values are in order. So we've already got those ordered. We now know that x tilde, the median, will be equal to, the fourth data value was 700,000 plus the fifth data value was 900,000. And we can divide by 2 to find the average of those two values. So the midpoint between those is just 800,000. So our median x tilde is 800,000. Okay, so let's now compare this median that we just calculated. So let's compare this median x tilde with the mean, which we calculated previously. So previously we saw that the mean for For the sample, X bar was equal to 2,209,375. So let's compare those two values, and I'd actually like you to pause just for a moment to think about this. How would you describe the relationship between these two values, and why is that true in this case? So whatever you determine as the relationship between them, why is that true for this example? So pause and we'll talk about it in a second. Okay, so we're comparing the mean of these football coach salaries to the median, and our mean was $2,209,375. The median is $800,000, and I would say the most glaring difference here is that the mean is much greater than the median, so it's a much larger number. Why is that true? So if we look at a set of data that we have, well, all of these salaries are, of course, humongous. They're really, really large values for a person's salary. But some of them are way out of the league of the others. So for example, this is almost 10 million. This is 9 million compared with a lot of the other data values in the set, 700,000, 440,000, etc. Potentially you could say that this 3 million is pretty large as well. But basically we have large data values that are pulling the mean up while they are not affecting the median. So those large data values pull up the mean but don't affect the median. The median is just based on the two middle values. It doesn't really matter how small the smallest ones are and how big the biggest ones are. All that matters is what are the two middle values. Whereas for the mean, we know that all the values are taken into account, and so if there are some values that are unusually large compared to the rest of the data, that's going to skew the mean up, versus if we have some data values that are unusually small, that would skew the mean down. These large data values are often called outliers, so we'll define outliers in a more specific way later on in the course. But we could consider this 9,255,000 as an outlier that is pulling up the mean but is not affecting the median. Okay, let me give you an example to try. So with this, before calculating, I'd first like you to estimate. So look at each set of data, and within that set of data, will the mean be a lot larger than the median? Will the median be much larger than the mean? Or will the two values be pretty close together? And secondly, for each data set, calculate the mean and calculate the median. So first, do a little eyeball about what do you expect the mean to be, about what do you expect the median to be, how might they compare, and then actually calculate those values. So again, pause and try it out, and we'll talk about it in just a moment. Okay, so first, before calculating, we want to estimate. Will the mean be significantly larger, or vice versa, or will they be pretty close together? So when we look at the first data set, we've got data that's pretty evenly spread out. It's not exactly evenly spread out, but we've already got this data in order, and it's around a center of 0. Here there's n equals 5 data values in the sample. 5 is odd, so there's just going to be one middle value. And in our case, x tilde, the middle value, is 0. Or in other words, the median is 0 in this set of data. And, well, we've already calculated something, but just based on estimating, it also looks like because the data is fairly symmetric around the middle, there's no really unusually large values or really unusually small values. We would guess that the mean might be pretty close to the median. So here it looks like the data is symmetric. In other words, similar on both sides of the center. And so it looks like the mean and median will be similar. So there'll be similar values. We won't have one being way larger than the others. We've already calculated the median because this is a really small set of data that was easy to do. Let's now calculate the mean. So let's calculate the mean, x with a bar over it. That's the sum of the data values divided by the number of data values. So in our case, that's -4 plus -2 plus 0 plus 1 plus 5 divided by the number of data values. So that's -4 plus -2 is -6 plus 0 plus +6 over 5. That's 0 over 5. And in this case, it so happens that the mean is exactly 0 as well. So, just so happens that the mean is 0 as well, that these two, mean and median in this case, were exactly equal to each other. And so our intuition was correct that it looked like the data value, the mean and median, would be similar values. Now let's take a look at the second set of data values. In this set of data values, we've got 1, 1, 50, 53, 54, 56. And we see that these data values are pretty close together, whereas these could be considered outliers. These are much smaller than the other data values that we have. So it looks like those small data values, those will bring down the mean. So they will bring down the mean x bar, and they will not affect the median, because neither of those is a middle value. It will not affect the median x tilde. So our guess is that the mean x bar is going to be way less than the median x tilde. That's our guess. Let's calculate this each value and verify that. So if we calculate the median, we know that we need to take the middle value. There's n equals 6. There's an even number of data values, so there's two values in the middle. The value 50 and the value 53 are the two middle values. So the median x tilde is going to be the average of 50 and 53. So that means that x tilde is the middle of those two values, 51.5. So x tilde is 51.5. What is the mean? So the mean in this case, the mean x bar is equal to 1 plus 1 plus 50 plus 53 plus 54 plus 56 divided by the total number of data values. And so we can throw that into a calculator and find that value. So if we add those values, we end up with 215 divided by 6. And when we divide by 6, we've got 35.83 repeating. So that's our mean, and we see that indeed the mean is much smaller than the median. So our guess was correct that the mean is much smaller than the median because those two small values, those two ones, are bringing down the mean but not affecting the median. Let's talk about why you might choose to use the mean or the median as a measure of center. So these are both very common values to represent the center of a set of data. A pro about the median is that it is not affected by outliers, as we saw above. So some data that you might hear about that is affected by outliers would be, especially in the US, salaries of individuals or home prices. So say in North Adams, maybe a lot of home prices are between $100,000 and $300,000, but there might be a couple of really amazing huge mansions that are worth $1 million. So that those couple $1 million houses would really throw off the mean or average home price, while the median home price is not affected by that. So the median price of a home is generally given instead of the mean. Similarly, if we're talking about American wages, whenever you hear about this on the news, typically they use median as a more representative measure of center than the mean, because again, you've got lots of people making, between say $30,000 and $120,000 a year, but you've got a couple, CEOs or actors or whatever making tens of millions of dollars, and those outliers really throw off the measure of center of what we would think of as a typical salary. Okay, so those are some reasons to use the median, especially in data that is not very symmetric, that has outliers. Why should we use the mean? The mean takes all data values into account, while the median only takes the middle one or two data values into account. So the mean represents more of the data. In most advanced statistical methods, the mean is used. We'll see later that the mean is typically used with the standard deviation, which is a measure of how spread out the data is. So in more advanced statistics, particularly when you're looking at data that is fairly symmetric, that doesn't have a lot of outliers, the mean is more useful and more representative. Let's talk about one last measure of center, the mode. So the mode is the most commonly occurring data value in a data set. The mode is obviously really easy to find. It's really easy to see, especially if you've got like a histogram or a frequency distribution. But it doesn't tell you a whole lot of information, so it's a very accessible measure of center that's not used as much in more advanced statistics. But let's look at these three examples and find the mode in each case. So in this first example, 2, 5, 9, 1, 4, 3, each data value occurs exactly once. So there's no one data value that occurs more than others. So this has no mode. Our next set of data, 2, 3, 3, 5, 6, 7, 7, 7, 8, 9, 9. 7 occurs 3 times, so 7 is the mode. 3 and 9 are also repeated, but not as often as 7 is repeated. And in our last example, 0 is repeated twice, 6 is repeated twice, so 0 and 6 are both modes. We would call this a bimodal distribution. So bimodal has 2 modes. We could also have a trimodal distribution if there are 3 modes, but we don't really go beyond that with, quadrimodal or anything like that.